a warm region, and despite it being a warm region, we can also have some strong freezing temperatures that come through from the south, from Patagonia. In terms of our average daily temperature, we have warmer temperatures during the winter and the spring, that you find commonly in Mediterranean regions such as Cordoba, Spain, or Madeira, California. Unfortunately, I don't have the Israel on here, and these would be daily average temperature values. And the same with evapotranspiration. Obviously, we have higher evapotranspiration during the winter and spring that we find in many Mediterranean areas. We have very much of a continental climate. And we have temperatures maximum above 30 degrees from maybe mid-spring until kind of the end of fall. For about 6 months of year, the Tmax is over 30 on average. The objective today is to kind of show some experimental kind of data. I think we've heard a lot about irrigation this morning, better explained than I could do. So rather than kind of go into a conceptual talk, I just want to give an example of some of our experimental results, looking at the effects of a moderate deficit irrigation and warming by +4 degrees during late winter and spring in arid Argentina on plant water status and reproductive development in young trees. These results are kind of partial, but just to kind of give you a taste of what we're doing. In terms of the materials and methods, we had 2 irrigation levels, a well-irrigated control in which the water that was consumed was replaced twice a week, and we also had a 50%. We also had a 50% deficit irrigation. So it was kind of a mild to moderate water stress that we were trying to apply in a potted experiment. We had 2 temperature levels, a near ambient temperature control, and we had a warming treatment that was +4 degrees C. This was done in open-top chambers, which I'll show you in a minute. And we were using the cultivars Arbequina and Cortina, which are very common commercially in Argentina. Today I'm principally going to be talking about the results for Cortina. And again, the experiment was conducted in the late winter and spring. The idea was that the plants had already gone through kind of a winter chilling, and it accumulated a good number of chilling hours. So the idea was in the experiment we wouldn't affect the flowering intensity. And the trees were 3 years old in 30-liter pots. Here you can see kind of an example of the trees themselves, which are about almost 1.5 meters tall, with about 1.5 meters squared of leaf area. And we have both kind of control chambers and then heated chambers. In the heated chamber, you can see kind of this long sleeve, which contains large blackened rocks. The rocks absorb solar radiation, and air is pulled through. The heated air is pulled through with fans into the chamber and goes out the top. And on cloudy days or at night, you can't see this very well, but we have space heaters. This is kind of the space heater. You go in the U.S., go to Walmart or go to Target and buy a heater for $20, just a very simple heater. And the air is just kind of sucked in or pushed from the heater, 2,000-watt heater, into the chamber. And the system has a feedback loop, so we don't exceed +4 degrees warming. And we follow the daily cycle. We're always at about +4 degrees, sometimes a little bit less, a little more, but on average, it kind of works out. And so we applied irrigation by weighing on consecutive days to replace water consumed. We weighed a subset of the well-watered temperature control trees and a subset of the well-watered warmed trees. In general, as you can imagine, the warm trees consumed more water. And the 50% irrigation trees just received 50% of their respective treatment, whether it was the 100 TC or the 100 T+. We just merely divided by half and gave them that much water. And so here we have kind of the daily average temperatures during the experiment. Apologizes for the southern hemisphere. So this is kind of mid to late winter. The start of spring would technically be the 21st of September around here. And so we see at the beginning of the experiment, we had fairly cool temperatures, with average daily temperatures around 10 to 15 degrees. And then by the beginning of October, by the beginning of spring, we mostly had average daily temperatures in the T plus up over around 30 degrees. So it was a challenge during the reproductive development of the plants, at fairly high temperatures, not crazy extreme temperatures, but pretty high temperatures. And just to give you some idea of the phenology, that the leaf bud burst and reproductive bud burst are near mid-August, beginning of September, depending on the year, and flowering is occurring around here. In terms of the stomatal conductance, I'm mostly showing you kind of physiological variables for the next several slides. And as you might expect, near the beginning of the deficit irrigation treatment, there was no effect. But in third, fourth, fifth, and sixth measuring dates, we see that the open symbols, the 50% irrigated plants, had lower stomatal conductance. When we rewatered, about 7 days later, there was a fairly strong partial recovery. If we waited a little bit longer, I'm sure the plants would have reached their normal GS values. So it wasn't a very strong deficit irrigation treatment, kind of what you'd apply commercially, for a regulated deficit irrigation or something along those lines. But the temperature effect, in contrast, tended to be temperature dependent. Here we see on a cool day near the beginning of it's actually still late winter, we see that the warmed trees have a higher stomatal conductance than the controls. As you were comparing trees that were, say, at 15 degrees centigrade with trees that were at 20 degrees centigrade. So at 20 degrees, the warm plants did better in stomatal conductance. But later on, at least on a few dates, we see that we actually get less stomatal conductance under much warmer conditions. We see, for example, for each of the irrigation levels, we see that the warm trees have a lower stomatal conductance than the respective plants at the same irrigation level. And we get pretty much no effect. The plants recover very quickly in terms of temperature. So the temperature response is really dynamic. It's really from one day to the next. In terms of stem water potential, the results are a little bit different. What we're kind of seeing is an additive effect in which both irrigation and warming have an effect, both of them driving down the stem water potential to a more negative stem water potential. So if we look in terms of the warmed plants, we see that both of the red lines, both of the warm treatments have more negative values than than the control temperature plants. And we see that the effect of irrigation is occurring for each level of irrigation. We see on the well-irrigated trees, we see the clear symbols most often being below that of the well-watered control, and the same occurs for the heated plants. So we're getting kind of an additive effect here. In terms of stem water potential versus midday air temperature, this kind of thing is used as a basis for irrigation scheduling, or can be. So what we see is that as air temperature goes up, stem water decreases by about 1 megapascal for every 10-degree increase in temperature. So over the entire range of our midday air temperatures, we see that water potential is dropping about 2 megapascals. And so again, that's the kind of thing that's used for, can be used for irrigation scheduling. In terms of sap flow, we're still working with these results. I'm a bit confused about the results myself, but basically, what we see, this was in for several dates, about 10, 12 days in September, 10 to 12 days in October, and then in November. On all 3 dates, we see that the warming treatment plants, which are both in red, had a higher sap flow than in the control temperature plants. All the variability was much more than we wanted. As you might expect, on the first date, where there weren't any effect in terms of stem water potential or stomatal conductance, we didn't see any effect of irrigation. We might expect to see some effect later on. Kind of my best guess is that we're not seeing an effect here of irrigation, and kind of my guess is that it's mostly related to the variability and the measurements. But there were some other things going on that I need to look at. That's why I'm still confused about the results. For example, the warm treatments were causing leaf fall, and other things were going on at the same time. So I have to kind of work on that and disentangle the results in my own head. But kind of my guess is that we don't see an irrigation effect, mostly because of the variability. We had three trees with we're using the Dynamax kind of energy balance system. We kind of wrap around the sensor with the thermocouples around these very small trees, and we had 3 trees that were wired up or hooked up, if you will, for each irrigation treatment, or each of the 4 treatments, 4 combinations. Kind of switching gears here and going into full flowering date, just to mention, this is Coratina. We saw that a much earlier flowering date, about 20 or 30 degree days earlier in the T+ treatments than in the control. This is pretty similar for what we see for about a 5-degree latitudinal gradient in Argentina. So it's something pretty much be expected. It was interesting to see it kind of experimentally, and so a lot of work that we've been doing is to kind of see experimentally what jumps out as being new, and kind of compare it to what you see over latitudinal gradients or for observational results by growers or by ourselves in the field. And we also see some here. We see an interaction effect in that under the deficit irrigation, the control temperature trees had the latest flowering. They flowered about 10 degrees later in the control temperature trees that were well irrigated, and so you get some delay due to the deficit irrigation. Coratina, at least in our region, is fairly well known for producing a number of parthenocarpic fruit, unfertilized fruit that are very small fruit, known as shot berries in English, that then fall, and they're not normal commercial fruit. And under heating, that greatly exaggerated the number of parthenocarpic fruit. Up to 50% of the fruit number was in parthenocarpic fruit, which obviously drove down fruit number quite a bit. And we see that kind of thing, not to that exaggerated an extent, but we see that kind of thing there in the field. Occurs a lot with Coratina, to some extent with Manzanilla de Sevilla, but not nearly as much of a problem. And so it's hard to extrapolate these results to other varieties, which, I mean, I think the reproductive development is very sensitive, and that a lot of it's going to be very cultivar dependent. Maybe the physiological part is less cultivar dependent, but that's something I think we really don't know yet. And so all these things need to be examined in greater detail. That's why I say this is kind of a snapshot. And what we see here in terms of fruit number, as you expect, in terms of normal, viable commercial fruit, the fruit number at the end of the experiment was much lower under the warm trees with no effect of irrigation, which we would kind of hope for in terms of a mild or moderate water deficit irrigation treatment. And in general, I didn't mention it, but in general, the soil water content, the relative water that you can extract was around 50 to 60% even in the deficit trees. So you have 90% in the well water trees and the deficit irrigation trees. It was around 50%, 60%. Sometimes a little bit less, but in that range. So it's not that surprising we didn't get a very large effect in terms of deficit irrigation on the yield, which was we're really hoping that you wouldn't. So to conclude, stomatal conductance is sensitive to deficit irrigation. I think that's something that we can all agree on. While the GS response to warming tends to be temperature dependent, for me that's a really fascinating thing working with temperature, because the results are so context dependent. I mean, it really depends on, you say, oh, it's very warm in my region. Well, how warm is it? It's cool. The temperatures were cool. So much on the temperature itself. Stem water potential shows kind of an additive response to deficit irrigation and warming, which should lead to in terms of potentially greater irrigation or greater water use, which not positive. Reproductive development appears to be fairly sensitive to warming, at least in Coratina. This was under both well irrigated and deficit irrigation conditions. So it's now that you can kind of irrigate more and kind of dream away the effect of the warming. If you have very high temperatures, even if the plants are well watered, there's some very sensitive processes involved, and some of you guys here in Israel know about that. Are doing a lot of good research on that. And I didn't mention, but I'm sure Alon wants to know that the flowering intensity didn't change with the warming, with the idea that the chilling hours were kind of accumulated before the experiment started. And so thank you very much for coming, inviting me. It was very much an honor to come all this way and get to see some of Israel as well. And for some of you know Cecilia Rousseau, who's kind of I'd say she's really the driving force in our group. Andrea is a younger researcher that originally developed these open top chambers, and so we've got a very small research group. So this is kind of our grain of sand in the desert, if you will, in terms of what we're doing. So if anyone has a question or comment, I'm more than willing to talk to you now or later. What's that? Yeah, this is my research. I'm now a co-author and all this stuff. Oh, sorry, I didn't explain this. Yeah, this is a town where I live or lived for a lot of years, Anillaco, and this is the village square. You can see from the front door of the institute. And the mountains in the back are about 3,500 meters, 4,000 meters. And I think the tallest peak in our province is 6,200 meters. So yeah, we're up there. We're not in the Andes. We're like before what's called the pre-Andes mountains. And yeah. Yeah, Dynamax. Yeah, exactly. No. Mm-hmm. It's a good question. I'm not enough of an expert on the anatomical part to really answer concretely. I'm not sure in these kind of younger trees if that would reduce the effect or not. What do you think? Well, the the trees themselves are young trees, so you're talking about the trunk is like this. Less. I think it was like 3 centimeters. So that's my thinking. And we do have I think we have cross sections. So something I have to look at. It was less. Yeah, it was about 3. So, but I need to think about those things. So, thank you very much.
Everyone, thank you for coming to listen. It's a pleasure to be here. Just want to introduce you to my students. We try to have a multicultural lab. I'm proud of. You'll see a lot of pictures of my students because I don't have many results. So just to remind you, this is like in the northern hemispheres, we have flowering in April, May, and we have fruit harvest depending if it's for fruit or oil in September, November, and then again flowering. And what the process we're talking about here is these buds that will later become inflorescences and flowers, and later on fruit. And when you look at this branch, this is a picture in May, so you see these new fruitlets being developed here. Then you see the branches continuing to grow, and these new positions here is where the next flowering will occur in the next year. So their fate, if they will make flowers or not, is something that we're talking about now. And you can see here in this diagram these new leaves. If you look close at them, you can see that they have 2 different fates. They either can remain vegetative, like here, or they can become an inflorescence, like here. The terminal meristem normally in olives remains vegetative, so it can continue to grow from year to year. So here we're looking at these buds at this time, so we can see the decision here is already to make an inflorescence. In the beginning we wanted to see when this transition happens, because in the literature they talk about it transitioning happening already in summer and the beginning of autumn. But we're looking here at the electron microscope. We see leaf primordia. This is the meristem. And basically nothing happened until late February. In October, you still see the meristem making leaf primordia. Only now in late February you could see some kind of new development here, these round structures that will later on become flowers. So this happens, this transition happens in the end of our winter, more or less. And in order to understand what genes are involved, just remind you that we used information from Arabidopsis, where flowering it's an annual plant, and flowering is controlled by a gene called FT, one of the genes that controls it. And if you look for mutants that are late flowering, it could be a mutant in this FT gene. And if you overexpress FT, then you get very early flowering. So this is from Arabidopsis, and this just to remind you that FT, or florigen, is an important gene in flowering. When we looked at the expression of FT in leaves, we could see an increase in its expression during winter. Winter. This is 1 year, and then this is the second year. You can see an increase, and between that, the expression was very low in the leaves. So this time of increase in expression is just before what we talked about before, this inflorescence initiation, which happens in late February. When we overexpressed FT together with a group in Spain, in olives you can get these very small plants, bushy plants that make flowers all year round. So they lost juvenility, and they basically flower all year round. This is when you have lots of FT all the time. So the working model is that winter increases FT expression, like we saw that FT was going up in winter, and we know that the FT causes flower induction. We did experiments using our phytotrone to expose olive trees to different temperatures. And we saw that if we leave the trees in winter in warm temperatures, 28 degrees in day and 22 in the night, they don't make any flowers. And if we keep them at 16, 10 degrees, they make plenty of flowers. So it seems that when we talk about winter, we're talking about cold temperatures in winter that are causing this. It didn't matter if it was in long days or in short days. And when we looked at expression of FT, this gene, we see that it's increasing in cold temperatures, and if you grow the trees in warm temperatures, it doesn't no FT and no flowering. Sorry. We tried because we know now that cold temperatures can cause flowering. We said, well, what happens if we give the trees cold temperatures in mid-June, which is the middle of summer in Israel, and we saw that we can get flowering in autumn if we do that treatment, and if we give it in September, we can cause also flowering much than normal. But if we give it in November, which is when the end of November, which is about now, and give it 89 days, then we get the best flowering. So basically, we can cause flowering out of season, but the rate of flowering was lower in when we did the treatment in summer compared to fall compared to winter. So basically, we could have a tree that has two flowering seasons by artificial winter and natural winter, and we can get trees that have both ripe fruit and flowering, which is normal for normal trees. So basically, cold temperatures are increasing FT, and this is causing flower induction. We try to find out what exactly is the temperatures that cause a flower induction, and this is by giving following trees. We've been following trees in different locations in winter. Here we see results for Barnea, but we have it for 4 other cultivars, and this is the level of flowering that we received in every year. In some years, the flowering was very low, and some years much higher. This is Matityahu, which is up north in northern Israel. So there, the winter is much colder, and we get much higher flowering than in Rehovot. Now, this is important because the price of this is the price of olive oil. We can see that this increase in prices, mostly from Spain, is because of warmer winters and drought. So it's important to understand this. And recently we tried to build a model that can predict how much flowering there will be, and the model is based on the fact that the optimal temperature is 11 degrees. So if you at 11 degrees you get the most cold units, and we measure temperature hourly, and then we calculate how much cold we get. When this is an experiment done together with Giora's lab, that we give, they gave warm temperatures during January for a short period, and this completely reduced flowering in different cultivars, as we can see here. So the warm temperatures at this period is enough to reduce flowering. What we asked is what is happening actually is in this experiment. Is this just less hours of cold, or does warm temperatures have a negative effect on the cold accumulation? And in this experiment, we gave trees the perfect conditions of 10, 16 degrees, and we also gave them pulses of warm temperature. So this is for I forgot 1 hour, I think. 3 hours, and this is for 48 hours. And we saw that if we gave pulses of 48 hours, even though the total number of cold temperatures was the same, we completely abolished flowering. So this treatment of 48 hours of warm temperatures during winter completely abolished flowering, even though the number of 16 hours of cold was the same. So this means that warm temperatures is having a negative, it's reducing the ability of cold to cause flowering. So our model is that basically the 11 degrees is the perfect temperature, but then just imagine that we have a sieve, and this is a snowflake, and we have to carry this sieve to a refrigerator and then leave the snowflake in the refrigerator and let it accumulate during winter by always moving it. But it takes time for this sieve to reach the refrigerator, and if it's warm during this time that it's moving here, then it's going to melt. So basically, if the temperature is cold, then we'll end up with a big snowflake, and if the temperature is warm, then until it reaches the refrigerator, the freezer, it's going to be tiny. So we think that's what's happening here. That there's a time between the accumulation of cold and it's or the first perception of cold until it's accumulating, and during this time, if it's warm, then we basically end up with nothing. And this is supposed to show how different warmer temperatures actually reduce this cold. So in the end of winter, we basically measure how much we have in the freezer, and if we have nothing, then no flowering, and if we have a lot, then we have high flowering. So this is the model that was developed, and it's more or less what I told you here, and it's published. And we see that the model more or less fits the data that we had about what we had about flowering of Balnea. We extended the model now for other cultivars. And in this site, you can actually put in your temperatures. It's in English and Arabic and Spanish and Italian now. And you can enter your winter temperatures, and it can estimate how much flowering you get. So here I put the temperatures from September until now in Rehovot. And we had quite warm temperatures, and basically, of course, if we calculate now the flowering, it's close to zero. So basically, no accumulation until the end of November in the Rehovot. I'm now in sabbatical in Vancouver, and there the temperatures you see are between 6 and 14 degrees day and night. And my suggestion is to ship the olive trees to Vancouver for 1 month, and then bring them back, and you'll get lots of flowering. So that, what? Okay. But we have to ship them back after. So this is about flower induction, but at this time there's no fruit, but we also looked at the effect of fruit yield. How much time do I have? So I'll just make this very short. High fruit yield, low flowering, and we see that FT goes up normally, but if you have high fruit load, FT is much lower. So we know that fruit load reduces FT, and this is what causes biennial bearing. and these are the people that worked on this. I just wanted to talk about one last thing, and that's gibberellin. So gibberellin is a plant hormone, and in many fruit trees, it actually inhibits flowering, and it does that by reducing FT expression. And Enrique, you're talking about what happens if you have many years of drought, and how to not to let the plant die. So I suspect that if you spray the trees with gibberellin, you won't get any flowering, so that will increase their survival until this drought ends. Although in Argentina, the levels of gibberellin that we gave wasn't enough to reduce flowering, so we need to give more than what we did there. In any case, here you see that you give gibberellin, no flowering, and we wanted to know if it affects FT, and basically it didn't affect FT. FT levels were increasing with or without the gibberellin treatment, even though the plant didn't flower. So we know gibberellin is now acting on FT, it's acting downstream. And we are looking for genes that are affected by gibberellin. And so we had here 3 treatments. One was this temperature, warm temperature that reduced flowering, and gibberellin, which completely eliminated flowering. And here are 2 genes that we looked at that seem to be affected by gibberellin and heat in January. So these are genes expressed in the meristem that increase in winter. But when you apply gibberellin or when you give it heat, then their levels do not increase. And one of these genes is involved in biosynthesis of trilose 6-phosphate. And we think that this sugar that's very hard to measure might be also very important in flowering of olives, and it's known to affect flowering in Arabidopsis. We actually took samples to measure trilose 6-phosphate, which is very difficult, to the Weizmann Institute, and the samples were there, and then the Iranians decided to eliminate the building, so samples are gone. But there are more tragic things in our samples. So yeah, so we think gibberellin is acting downstream by these genes and probably many more genes. And this specific work was done together with Giora, and these are Idan is a major contributor here, but also Taher and Volcani. Thanks, and this is work is done by funding by the Ministry of Agriculture. Thank you. So I need to just repeat the question. The question is there any known variation between cultivars about their requirements of code? So yes, so we did, I mentioned we looked at 5 cultivars, and Askal, which is now becoming more interesting in Israel, is actually one with low chilling requirements. So it flowered really well in winters that Balnea and other cultivars did not. And regarding the molecular mechanism why it's so we still don't know that.
Okay. Yeah, so thanks, Arnon, for letting me sharing the results that I have with you. And today I will speak with you about the effect of high temperature on olive oil yield and quality. So this is, of course, the work of many great people, collaborators, as well as workers, lab manager, and many students. So this is, maybe you already saw it. This is from NASA website, the temperature during the last 150 years with a scale from blue to red. And you can see here, and just concentrate on the region of the Mediterranean, which is the main region of the olive cultivation, and see what happened in the last several years. So yeah, definitely we do have climate change, and it has many effects on all plants as well as olives. So in the olives, the annual cycle, high temperature affect many different stages. Alon talked about the high temperature during winters that reduce the flower induction. High temperature during spring will reduce the fruit set, and high temperature during the summer will decrease the oil yield and quality, and this is what I'm talking today. So I just took the temperature on Beit Dagan in Volcani Institute in the last 20 years, or from 2000 to 2020, and just analyzed them, but separated it to different seasons. And I looked on the trend line of the maximum daily temperature and the minimum daily temperature. And as you can see here, in the winter, the temperature raised in about half a degree, in the spring in 0.8, but in the summer, more than 1 degree in 20 years. That's a lot. So what we did is that we took I was, by the way, born and raised in Bet Shan Valley in a kibbutz called Tirat Tzvi in a very warm weather. And we took the 5 cultivars that already grown there. And from each cultivar, we had 12 5-year-old trees in 60-liter pots. And right after fruit set around mid-May, we splitted them from Volcani. We took half of them, 6 trees from each cultivar to Tirat Tzvi and 6 to Tzuba until the end of the season, where we brought back the trees to Volcani. This was the temperature, and Peter talked about different temperatures. So here we see in Tirat Tzvi that in most days the maximum temperature was around 45, the minimum 25, and in Tzuba it was between 35 and 15, something like that. This is 2016 and this is 2017. And you see here more red because the experiment in each season was finished when the fruit was in maturity index of 2.5, and specifically in this year, I'm not sure why, the Coratina and the Barnea riped late. So this is what we had in both years. The Barnea show tolerance to high summer temperature, and in the end of the season it has the same fruit size and the same oil concentration in Tirat Tzvi as in Tzuba. On the other hand, the Koroneki was very sensitive, and in Tirat Tzvi we had smaller fruit and lower oil concentration. The Coratina had lower fruit size but the same oil concentration. The Suri, as the Koroneki, was very sensitive in both parameters, and the Pichulin, as the Coratina, had an effect only on the fruit size but not on the oil concentration. We also looked on the cell size and cell layers, and we saw that in September, the differences between fruit size is mainly due to cell size. As you probably all know, in the double sigmoid, it's known that in the first stage, the fruit development is mainly based on cell division, and in the second, mainly on the cell expansion. And what we saw when we counted the number of cell layers is that in Bornea, which is tolerant cultivar, we could see that in the end of the season, when it get a bit cold, it has many cell division. It may be this is one of the mechanisms to overcome the negative effect of the high temperature. This is oil drops in the mesocarp, this is the exocarp, and this is the mesocarp in Koroneki, which is sensitive, in Tsuba and Tirat Tzvi. And as you can see, in the beginning of June, you even see more oil in the fruit in Tirat Tzvi because it was warmer and it's still spring. But when it gets really warm in July and August, you can see that we get much more oil in Tsuba compared to Tirat Tzvi. We looked on the oil quality in two parameters. One is the total polyphenols, and the other is the percentage of oleic acid. And in all cultivar, in both years, we found that in Tsuba, we got higher polyphenols and higher oleic acid in all cultivars. However, in Suri, we can see that the differences was pretty low. Therefore, we marked it as high temperature tolerant in terms of oil quality. Koratina and Koroneki was sensitive, but Bornea and Fishulin actually, according to the IOC category, cannot be called olive oil because the quality was really bad. It need to have at least 55% of oleic acid, and both cannot be characterized as olive oil. We also looked on all genes involved in oil biosynthesis, and we found many genes that are high temperature sensitive. Probably, therefore, we get less oil in warm temperature in the summer. And we also found two markers that can mark us the tolerant and the sensitive cultivars. So to summarize the results that we had, we used three parameters: fruit weight, oil accumulation, and oil quality. The Bornea show tolerant in both fruit weight and oil accumulation, but not in oil quality. Fishulin and Koratina were tolerant in oil accumulation only. Suri only oil quality, and Koroneki was sensitive in all three parameters. In the third year, we again did similar experiment. However, in this year, we only used 24 Suri trees, which was sensitive. We divided the 24 trees into 6 groups of 4 trees. One group was located in Tsuba for the whole season. One group was located in Tirat Tzvi for the whole season. And the other 4 groups were moved to Tirat Tzvi for 1.5 months and then returned to Tsuba, each group in different periods. What we found is when we looked on the fruit weight, we found that all the groups that spent 1.5 months in Tirat Tzvi, no matter when, got lower fruit weight compared to the ones that spent the whole season in Tsuba. However, when we looked on the oil concentration, only one group was lower than the control, the blue one. Only this, which is group D. When we look on the oleic acid percentage, also again, we found that D, group number D, is similar and low percentage of oleic acid to the one that spends the whole season in Tirat Tzvi. So it means that in terms of period, the critical period for the negative effect of high temperature is between the beginning of July till mid-August. And then we wanted to know if the critical temperature is the maximum or the minimum temperature. Therefore, we did an experiment in 2024 only in the critical period between July 1st to August 15. And here we used convirons with 4 different conditions. One with condition of Tirat Tzvi-like, 45 maximum and 25 minimum. One Tsuba-like, 35 and 15. And the other 2 were mixed. One was Tirat Tzvi on the day and Tsuba on the night, and the other was the opposite. And this is what we found. So in terms of fruit weight, we found that, as you can see, the two columns that were maximum of 35 had much higher fruit weight on harvest compared to the one with 45 during the day. We got the same picture for oil percentage. Again, the two that were maximum 35 were much higher than the two with maximum of 45. Here you can see again the oil drops 45, 45. You get much less than 35 and 35. Okay, even if the minimum temperature is different. And this is the last. We look on the oleic acid percentage, and again, and look here on the percentage. As you can see, again, 55 is a minimum. This was 35. 45, we had less than 55, something like 50. And actually, the lowest one was 45 in the day and 15 in the night, which means it's not only the high temperature during the day, but it's also the difference between the day and the night that cause low oleic acid percentage. Again, this is less than 45% oleic acid. It's really low. So to summarize everything, what I wanted to say is that the day's heat waves, or the maximum temperature during the day, during the period of July and August, this is a critical time when it's reduced oil yield and quality. And that's it. Thank you very much. Taller. Mm-hmm. No, no, we didn't do it. The question was if we did some gas exchange test, and sorry, we didn't look on this direction. Can what reach the oil? Yeah, so yeah, again, it's from the beginning of July till mid-August. That's the most critical period, and this is also the most the period where the oil biosynthesis is highest. So it really makes sense. According to the IOC, olive oil must have at least 55% of oleic acid. Okay, and there is specific percentage also for the other fatty acid. And in the Barnea, which grown in Tirat Tzvi, we didn't get it. So it cannot be characterized as olive oil in one specific year, not in all years. Yeah, but anyway, in most cases we just don't check it. That's yeah. Yeah. Anyways, the Arbequina is worse, so at least we can. You will not die. Yeah, don't worry.
Okay, I think I'm following up with Giora with something we've observed almost accidentally. I did my PhD, I did the supervision of Arnon and Uri and Amnon. And I'm working on plant nutrition ever since. I'm not studying olive nutrition anymore until they came with a really interesting phenomena, which I will describe momentarily now, which is this dark pulp that occurs mainly in Ascal variety. Early at the season, you can start see it around September, for sure October. It's very, very common in Ascal, and we always call it, you have the fungi. You have a disease. This is how we called it back in 2010 or so. And I forgot all about it, and I'm working on avocado, and I work on vines. And again, this came to my table 3 years ago. And what is the motivation? The Ascal is very unique because it's very, very productive. And Giora just mentioned that it has low chilling requirements. It has extremely high oil content. We measured often 30% oil in the oil mill when it's harvested late in the season or at ripening, so around November. But the free fatty acid concentration increased rapidly, very, very early in the season. Mid-October, you start to have very high acidity, free fatty acids increase, and that's why farmers harvest it completely green, immature, when it hasn't reached the potential yield. Way, way before, at oil content of 20-22%, while the potential is 30%. That's a huge gap. Like others, I've been working with Nir Kilman, the farmer from Tabakama, and he states, I quote, "This variety, even when it harvests premature, leaves the highest amount of oil per hectare, more than any other variety in our environment. It's also suitable for super intensive systems, so it's very, very interesting. And if we'll be able to understand what this is, so maybe we will be able to prevent the increase in acidity, in free fatty acids. So 3 years ago, we got the main agronomist, Reuven Birger, Nizar, and Nir. They came to me and said, there's no fungi there. We've been looking for a fungi for 10 years, and there's none. But we did mineral analysis and look at clean fruits. We have less phosphorus. We have much more calcium. At fruits with this, we call it olive browning disorder, okay, olive browning disorder. We have more phosphorus and we have much less calcium. This is based on one sample, okay? They just analyzed fruits with or without symptoms. So we came to realize that that can be calcium-related disorder, like we have in vegetables, in tomatoes, in pepper, we have the blossom end rot. In apple, we have bitter pea. In avocado, we have internal gray pulp, which is what we've been working on in the past 5 years. So can calcium or calcium-related disorder reduce the oil quality in olives? And when you think about it, it only makes sense because the Ascal, because it's very fast growing and accumulates oil very, very early in the season, it's being harvested in September, meaning oil accumulation starts at mid-summer. And this is the period of time when fruits is more susceptible to calcium-related disorder. And we already showed in tomatoes that 8 Celsius increase in temperature reduce calcium accumulation in the fruit by 50%. the warmer it gets, the less calcium is deposited in the fruit, and more calcium is mobilized to the leaf, because the leaf water potential is lower, is more negative, and it absorbs all the calcium. Less calcium is available and less calcium is deposited in the fruit. And that's why all these calcium-related disorder occurs in the summer. Okay, bitter pit, and it's in apples and blossom endrol. This is all happening in summer. So is that what's happening in Ascal or in olive in general? Okay, this is another example that calcium is very important. The internal gray pulp is associated with low calcium concentration. If we have enough calcium, we have perfect avocado in this case. So to study this, we did a survey in Sabar Kamal, like everybody else, in central Israel, in a big plot of Ascal. And we monitored over 50 trees for 3 years. We harvested the trees, determined the yield, the olive browning disorder, and oil content and free fatty acids. This is how we determine the olive browning disorder. The index 0 means clean pulp, 1 means moderate symptoms, and 2 means severe symptoms of this olive browning. So this looks very similar to Giora's picture. You see completely healthy. You can't see my marker anymore. To your left, healthy tissue, and you see the cell is intact and it looks perfect. While when you have olive browning, you see cells that are damaged, and you can even see oil bodies that are completely deformed, and it seems like the oil is simply spilled out of the oil bodies. Just only makes sense. That's why we see oxidation early in the season. So the third thing we realize is that fruit size have a tremendous effect on the olive browning disorder. Fruit size is actually fruit load. Okay, when you have high fruit load, you'll get small fruits. When you have low fruit load, you get big fruits, large fruits. And we see that olive browning disorder is positively correlated to fruit size. Large fruits, we see a lot, very high OBD index. Small fruits, it's nearly 0. Okay. Another thing we realized at this time, about 2 years ago, that it's not only Ascal. When you start looking for it, like electric car, all of a sudden you see it everywhere. So we start cutting olives at maturity, and we see it in Manzanillo, and we see it in Lachino. And there was a brilliant student working on it, JP, and he also found it in South Africa in different varieties. So that was very interesting thing to see. It's not only Ascal. And Arnon Dag did an experiment on Manzanillo. So we had a fruit in Gilat. We did the same for Manzanillo, and we see the same trend. We see that large fruits, now Manzanillo is much larger than Ascal, and the olive browning disorder is lower, and still we see very solid positive correlation between fruit size and this disorder. We took advantage that we have in the background the olive cultivar collection of Arnon, and we went outside late November, and we tested different varieties. And since we saw that larger fruits are more browning disorder, we thought maybe it will be common to many different cultivars, but that was not the case. You can see that Picual, for example, that has very large fruit, 9 grams per fruit, has nearly 0 olive browning disorder, while the Ascal, which is relatively small, around 3 to 4 grams per fruit, have the most common, the most severe olive browning disorder. So fruit size within cultivar, it works great. But between cultivars, it's different. I mean, it's not only fruit size, there's something else in it. You see some varieties that we could not ever see olive browning, like Barnea for 2 years, Picual, and so on. So is it related to, is it related, yeah, to the increase in acidity? We harvested Ascal. This is just an example for one of the 3 years. Very, very early, late August, and you see that already at that stage, we saw the browning disorder, and we saw a significant increase in free fatty acids. And when we go later in the season, acidity increases, and the effect of the OBD is more severe. You can also see it in the cultivar collection. Cultivars that don't have OBD have very good oil or low acidity, while cultivars that show high OBD severity has very high free fatty acid concentration, indicating that free fatty acids is very significant, or that OBD has huge effect on free fatty acid concentration. Going back to calcium, we hypothesized that calcium is related, or is low calcium concentration is the cause for OBD. So we took fruits with no OBD, and we saw that calcium concentration is nearly double than fruits with moderate or severe symptoms of OBD. We couldn't find an effect on the tissue itself. So the tissue that show the symptoms have the same calcium concentration as the tissue next to it that doesn't show it. But if the fruits has olive browning disorder, calcium concentration is significantly lower. And you can see it here, the negative correlation between OBD and calcium. If you have high calcium, you get low OBD, and vice versa. But it's not only calcium, as you can imagine from this figure. There's a big cloud with very high variability. And what we also found that nitrogen is positively correlated. Actually, that's a problem, because there's a lot of autocorrelation between different minerals in the fruit. Nitrogen and phosphorus always go together. And how can you know which is which? So what we did, we took the whole mineral composition of the fruit pulp and the OBD and the free fatty acids into a statistical model that says nitrogen is dominant, and the more nitrogen you get in the fruit, you're gonna get more olive browning disorder. Second most important is calcium, and there's of course negative correlation between calcium and OBD. The more calcium you have in fruit, the less you're gonna get OBD. But also magnesium, boron, sodium, zinc, and so on and so on. And again, the problem is that there's a lot of autocorrelation between different nutrients. And what JP did using the statistical model, saying what are my chances to have OBD depending on the nutrient composition of the pulp. So you can see here, if you have high nitrogen level and low calcium level, the chances is very high. You're going to have a lot of OBD and vice versa. Low nitrogen, high calcium, low chances to have olive browning disorder. So we first define this interesting phenomena that apparently is not limited to Ascal only, although Ascal is by far the most, where we saw the most common and the most severe symptoms. And it is a nutritional related disorder. but probably that's not the only thing. For sure, there's a kind of genetic basis to it, because we saw that with the same nitrogen or the same nutrient composition of the pulp, different varieties will have different impact. We saw it in quite large number of variety, nearly between 30 to 40% in the cultivar collection. Nitrogen accelerate OBD, while calcium reduce OBD, but there's it's more than just nitrogen and calcium. It's a more complex system. For sure, weather will affect it, but weather also affect the composition of nutrients in the pulp, and this is what we are talking about here, climate change. The warmer and the drier it's going to get, you'll find less calcium in your fruit. Doesn't matter if it's cherry, apple, or olive. And eventually, if you have olive browning disorder, you'll get bad development of the cells, and you get bad oil quality, and that's the problem. So I want to acknowledge the people that assist me. Nir Kilman here from Sabar Kama Farm that helped us a lot with everything. My lab teams, Adi, JP, the students that did most of the work, and Ishai. Arnon Dag team that extracted the oil and did all the oil quality analysis. Ilana Stein for the sectioning. Yeah, and there's only one acknowledgement missing is the founder, which I failed to find for 3 years. So I have no one to thank. And thank you. Looks like it, yeah. Not directly. I think it's just, well, the sequence of event is that the cells collapse, and then the phenols exposed to enzyme or to environment that it's not supposed to, and then it's oxidized, and what you see is this brown. Yeah. Yeah, is there any fertilization management that can reduce the problem? What we are trying to do now with the guy sitting next to you is to give nitrogen until fruit set. So to reduce the nitrogen content, to have enough nitrogen for the spring flush and for the flowering, and not supply as much nitrogen during food development. And then we want to see how can we manipulate the fruits to have more calcium. We are trying to do it with polyphosphate, which is source of phosphorus, and chelate for calcium. We failed to do it in olive. We have excellent result in avocado, so we can get more calcium in the fruit. Any manipulation, if you give nitrogen, don't give it as ammonium, give it as nitrate. Give as less potassium as you can, so there will be less competition with calcium, and you'll get more calcium in the fruit. Arnon has some experiment with foliar application of calcium. I don't know. It doesn't work. Yeah.
The last two presentations will be people coming from the field. And the first one will be Yizhar Tugendhaft from the Israeli Bioorganic Agricultural Association. He will speak about intensive olive cultivation in the Negev Desert for 30 years perspective. Yizhar involved in olive cultivation in this area for many, many years, so we have a lot of experience, and will share with us his experience in this topic.
Thank you. Thank you for the invitation to speak at this important event. I am also a student of Arnon. My PhD was done under Arnon's supervision, so it seems that there's a legacy already. I was asked to describe what happened in the olive cultivation in this region, in the Negev Desert, for the past 30 years. So I have roughly 5 minutes per decade, so I will be very brief. This is not a scientific presentation, rather agronomic and historical review. So I'll try to describe what has happened in this region. Just to let you know, to point out that olive cultivation has started here many years ago. This is a remain of a Nabatean field, so to speak. It's a Nabatean terrace, I think 12 kilometers to the south. And the Nabateans grew in this region olives, grapes, cereals, all rain-fed. They knew how to harvest the rain and manipulate that. This knowledge was, I guess, rather forgotten, or this area got dehydrated. 1943, first Jewish settlement in the Negev area. The people of The people of Revivim bought some land in a sludge area about 10 kilometers to the north of us, and they started to experiment in local agriculture. So they drilled to look for water, and they found brackish water, and they started to grow things. And one of these things was cultivation of olives. So the first range or agricultural knowledge of growing olives under saline or brackish water, talk about 4.2, 4.5, that's the Siemens per meter, was achieved in Revivim. This is the first building that I will get to it in a minute. This is the first building that was established for this settlement. We skip in time. Late 1970s, early 1980s, there was trials to find oil. So the government and private entities were drilling in this region for oil, deep drills, and they found water. Brackish fossil water. It was published by Yizhar in 1985, and the discovery was rather huge aquifer, fossil aquifer of water with changing salinity. I think the depth of the drills was something like 700 to 800 meters. But this gave the idea and the initiative to develop a vast agriculture with new resource of water. So later on, an initiative of the Jewish National Fund and the Ministry of Agriculture to expand agriculture in the Negev area, Negev and the southern part of what we call Arava. It's the desert part of Israel. So again, Kibbutz Revivim was one of the pioneers and planted, with the help of these bodies, planted 100 hectares of olives, irrigated with saline, or we should say brackish water. Later on, this I would say success, agronomical success, was described by Zeev Weizmann. The research and the data gathering was following with the development of agricultural activity. Farmers did, and the research was following to understand what is going on. And 9 years of experience showed that we can grow, this is Bonnet, but other varieties as well. We can grow it on under conditions that considered non-economical for olive cultivation or other orchard crops. So that was 2004. And Weizmann predicted a reasonable period of years with relatively high productivity and high oil quality. I was at the time already working at Revivim, and indeed yields were high and the oil quality was fairly good. We considered that at the time very good olive oil, and the economic aspect and the consumption of good quality oil began in Israel at those years. We started to produce good quality oil. We started to talk about extra virgin. We started to talk about tasting oil, tasting panels, and organoleptic aspects, and so on. So that was, I think, was available and achieved with the fact that there was water for agriculture. Later on, people continue to plant, continue to develop with the help of the state. By 2008, there was 700 hectares of olive plantations in Ramat Negev area, which is quite significant volume for such a small country and such a dry area. Arnon published in 2008 a review of this activity, and the results were really good in terms of quality, in terms of yield, in terms of profit for farmers. But, and that's why I'm standing here now, the reasonable period of time was about to end. And we noticed that the plantations irrigated with brackish water are declining. The quality is declining. The vigorous of the trees was reduced. The quantity of the oil was reduced, and so on and so on. So people do the math. The farmer doesn't want to lose money, so it's difficult to see, but this is an uprooted olive growth, because the economics was against the the agricultural activity. So what we see after a very long time use of saline water, I think you all know and you're all familiar with this phenomena. Soil compaction, reduced hydraulic conductivity, the soil disperse, and eventually we lose money. So what we do, I will show now briefly two directions of what was happened here. One is altering the source of water from brackish water to effluent water, recycled water, treated sewage water, you name it, it's all the same, to irrigate the olives. And that made, in my perspective, big change in this area. We start introducing organic amendments to the soil. We start to leach the salts. The entire environment of the roots is changing, and it changes quite quickly, to my opinion. This is the plantation I'm in charge. I'm working in. I'm managing. We are now harvesting, so you are all invited tomorrow morning to take a morning walk on the what you call it? טיילת. איך? מה שאמרת? Promenade 5 kilometers to north and come and see the olive harvest in this plantation. The thing is this, very quickly, I think this was done, this soil sampling was done roughly 18 months after changing the water source. So I just wanted to show you what happened 50 centimeters across from the lateral, from the irrigation lateral, represent to me what was the situation with brackish water. One can argue, is it really accurate? But I think it's a demonstrate the phenomena. So once we give much better quality of water, we can see that the percentage of saturation rises. The electrical conductivity is declining, and the organic matter is quickly jumps up in the root zone, which is really important. And this is only from the water. Another aspect, another direction that I would like to show here, I will explain this this slide. I apologize, it's from the right to left. I couldn't find the way to flip it, so it will be convenient for you. But what I'm showing here is from 1980, very small plantations of olives in this region, irrigated with fresh water. Later on, settlers started to plant olive plantation with saline water, and a very quick expansion. And what they did is either change the water source or uproot the plantations. So from roughly 700 hectares at the peak, we're now cultivating, not only me, but the settlers in this area, less than 400 hectares of olives. And this is all economics. Still, what can we do? What we want to do? One thing is to increase the income of the farmer. We can and we should look for alternative or additional income sources. like harvesting energy from the sun directly to electricity, harvesting energy from the sun to produce oil. It's the same thing. Sequestration of carbon is something that has some commercial value. This can be trade, tourism, and so on and so on. So it is not just to grow olive or just to be a farmer. We need to change the way we think. Another thing that we can provide as farmers who grow olives in the desert, not only here, I think in many other deserts in the world, is to sell environmental services such as recycling water, recycling sewage water, otherwise going I don't know where. So the olive can give us a good solution to many things, not just the olive oil. Okay. And to conclude, we can sell ecological services. We can transform the desert soil into arable land. And we can have some additional income to rural communities elsewhere and also here. Thank you very much. Main limitations to grow olives at Ramat Negev is the availability of land, availability of water for irrigation, and the way you manage to have a profit. So these are the main limitations. If we're talking about general aspect of the limitations of growing olives in deserts, I think it's the availability of irrigation water. This is the most important thing. The shading of electrical panels over the canopy of olives, we don't know yet. This should be studied. My gut tell me that reducing the direct radiation on the canopy of the tree will give us some additional benefits. We heard earlier about the effect of the warming of the canopy, the temperature of the fruit and the leaves and the buds of the tree. I think we can have symbiosis in this phenomenon.
There is a big issue regarding the use of soil and water for irrigation in Israel. Alon was involved in this topic a lot. People of the R&D Negev, Ramat Negev have done this. And I think, and correct me if I'm wrong, that currently the main belief is that you cannot have sustainable agriculture with so high salinity. You need to take out the salt before you bring it to the field. You load the field with more and more salt and you will pay the cost eventually. So Yizhar is saying we are happy to change to better water, and the better water are reclaimed wastewater that in other countries considered to be low quality water. In Yizhar perspective, it's good water. So it depends on your alternative, if you have alternative or not. If you do not have alternative, even reclaimed wastewater is good alternative. Yizhar, thank you very much. So we are moving from Israel to India, to Rajasthan. There is very unique and interesting test case of growing olive in Rajasthan arid area. And Yuval Chen is working with them for many years, and he will share with us his experience in growing olive in Rajasthan.
Before we start, I would like to speak about 3 different issues. One of them is the project in Rajasthan, but the 3 issues are, first of all, how to introduce olive crop to a new region. I think it's very relevant after everything we hear here. Just to put us in a perspective, olive oil world production in 2004 was about 3.2 million tons. Today, we are struggling to reach 3.5 million tons. So it means that the olive production worldwide is not increasing. Should have been exceeding the 4 million tons. So climate changes is here, and this project is proving that. But let's talk about introducing olive crop to a new region, because this will be the future of olive cultivation from my perspective. So once we come to a new region, the most important thing is to study the climate. Usually, we don't have the time to study the climate, so we need to guess, and we are gathering information, but what is important is hourly collection of temperature throughout the year. Because without that, we will guess. The second thing is to introduce as many varieties as possible, because each olive variety is behaving differently under different climate. So let's talk a little bit about the project in Rajasthan, and last we will speak about what happened to the climate since we have started. So this was a very ambitious project. It was a PPT, it's private, public partnership between 2 companies, the private and the Rajasthan government. And the mission was to produce the olive oil for consumption in India, which when the project started was about 1,000 tons, and in 2023 it was about 20,000 tons. So there is an impact of the project already. These are the partners. The project layout was 6 farms of 30 hectares all over Rajasthan, 1 farm of 2.5 hectares. It was very much similar to the farm in Revivim, because Revivim initiated the project. I took over after 1 or 2 years, and we have started to study. These are the locations. So 3 or 4 years after the beginning, we started to have fruit. So we were very happy. Rajasthan was good for olive cultivation. We established a nursery. We started local production of plant. First it came once we saw that there is a huge problem of nematode in India, small root system seedlings, all made in India. Early stages, I cannot say anything special about the early stages of the project, because things more or less progress normally. We had the first production 2014, 2015. Inaugurated the factory, everybody was very happy. But things were not so easy. Because we started to see difference between the different farms. Some farms yield, some farms didn't. So there is a question, what are olive chilling requirements? I don't know if any of us who works with olive, does each variety require the same chilling hour? For this we have And could we synchronize the flowering of pollinators in different regions? Because some varieties flowering in different periods of the year in different regions. I'm talking about Argentina, India, Peru, Brazil. Everywhere, varieties behave differently. So these have to be taken into consideration. So once we started to have difference, we started to study the climate. We collected hourly temperature. Just randomly, we decide to check temperature below 10 degrees and temperature above 25 degrees, which is very much similar to what Alon was saying. So in our we have that much hours below 10 degrees during the October-March period. Had less hours, but had more fruit. So, like olive, nothing is really clear why it's happening. At the same time, we checked how many temperature above 25 degrees we have in this period. And after what Alon said, I can say that this is for the success of a project. It's still the same. Almost double number of hours above 25 degrees. So we have compared the west farm and the west farm. The bottom one is compared with one here. You can see that much less hours above 25 degrees compared to Centro. And at the same time, there's much more hours below 10 degrees compared to Centro. So this area is actually giving us the chilling hours that we have not less. And as a result, the appearance of the plants is much different. High chilling hours every 5 minutes. What came at the same time. We had very, very strange phenomena, also branches that developed during the winter flowered in some years. So it was a very, very big laboratory. So after this result, we started with less attention on again, there was some formula that you need to have some hour below 7 degrees, which is not. You go to Lima, you have between 14 and 18 degrees, and every year you have flowers. In Ica in Peru, temperature vary between 10 and 18 during winter, and also there's a big flower. It's a different story because during the winter in Catamarca region, which is not as good as we have what we call veranal. It's high temperature during the winter, and in here that we have many days like this, there are no flowering or very little flowering. Now let's talk a little bit about climate changes. These are 15 years accumulation of hours. So these are hours above 25 degrees in our 3 best parts. So let's just look at November. What the tendency is to increase the number of hours above 25 degrees. In the first months of winter and the last and shorter in India. When we look at hours below 10 degrees, the same tendency. You see that in healthy farms, in this period, we have so much less hours below 10 degrees. This is something we need to think about when we go to a new region, because there also will be some climate changes. If we are on the border, and this is first sight impression. Filtration process completed, and turn into vegetative growth. To conclude, where are the areas to grow olives in Pakistan or in India as a whole? North of this line, Iowa, Buchanan, up to the also, if you go a little bit to the west, now, this is very important. Talk about the quality of the oil and define something very important. In India, the climate, you have a short winter, even shorter spring, and then we have the summer. But the summer is happening from mid-April to mid-June. We have very high temperature of 45 in the morning and 38 in the night. And then when the monsoon comes, we have a moderate temperature. And you see the oil quality. High temperature during July, August, and not in early stages. Argentina is the same. Once we have hot summers, we have more defect in nucleic acid. The winter are expected to have the same result. In summary, the climate is one factor. It's very, very important to adapt the right agronomic practice that will follow the climate, and not to try to look for one formula to grow olive everywhere. It's very important to keep the plants from vegetative growth. We need to keep the plants smaller all the time. In other climates, you have to be worried about other things. In Argentina, you have to be worried about the frost. Any place you need to, but you need to be aware to the climate all the time. This is it, more or less. This is Yunus. Any questions? Well, there was a natural course. The one who are above this line are more here, the one which are below. It's not that it's impossible, it's more difficult. There's also another problem in India which I didn't mention. They're getting the water from the canal. And the canal is closed between April and mid-May. This is during flowering fruit set. So many of the farmers just don't have enough water to support the flowering. We have flowering almost everywhere, but only in the very north part we manage to keep the flowering and to have it. That's the main issue. For maintenance, because there is no during the hot season they're not well. Last 30 years they're closing the canal. There are more than one thing. It's huge. 10 times the Jordan River. we had successful with 4 varieties, which is the Koroneki, Barnea, Coratina, and Arbequina. We had fruit in the very north in Frantorio as well, and Fisholin Maroki, but not by chance we had some flowering, not heavy crop. Koroneki performed very well, and Barnea also very well. No. No, there's 1,000 hectares planted. The nursery worked very well and plant distributed to farmers, but many in Gangalaga, which is, I don't know if you remember, Baro area, Anuka, from there to the north, farmers having fruit. But they have some fun ideas. They read about Spanish agriculture. You don't have to irrigate and say, oh, this plant fertilizer is good. In some part of the world they can grow all of this out. So once we left, they stopped fertilizing, they stopped. No, but they are really, I don't blame it. Sorry, that's the argument.
Okay, thank you, Yuval. Thank you all for staying until the end, and thank you for all the speakers. Thank you.